For the last 2 weeks, we've been focusing on normal form games where everything happens simultaneously. That's a very important class of games for various reasons. But of course, in practice, most games in many real applications have some kind of dynamic structure where play evolves or kind of takes place over time. And the game goes through a kind of sequence of states, and players can make observations of the current state and respond to it. So the usual formalization of this is called extensive form, which is the main topic of the next 2 weeks. But in this first video, we're going to do a warm-up where we talk about a restricted class of sequential games in a more intuitive way without a kind of mathematical formalization. So this is meant as a sort of warm-up. So imagine this scenario where first we have a first player who has to choose a move from a set of moves, and then we have a player 2 who moves second. So player 2 is going to observe what player 1 did. So player 2 is going to observe player 1's choice, and then they're going to make a choice of their own from a set of moves. And then payoffs are going to be given by just a normal payoff function. So given a choice of move for both players, then both players get a real number payoff. Now, strategies for a game like this are not the same as for a normal form game, specifically because player 2 is able to make an observation. So a pure strategy for player 1 is still going to be just the same thing as a choice of move. But a pure strategy for player 2 is going to be a thing called a contingent strategy, which is going to be a function from observations to moves. So that is to say, the set of pure strategies for player 2 is the set of functions from X to Y. So what that means is that a strategy profile, a pure strategy profile for this game is going to be a pair consisting of an element of X and a function from X to Y. That is to say, player 2 strategy has to say what player 2 will do, even if player 1 makes a choice different to the one that they actually make. Okay, now we can sort of solve this game by an important method called backward induction, and we're going to come back to backward induction a lot, but this is a kind of first introduction to it. So the idea goes like this. Suppose we are player 2 and we've just observed some particular move, call it small x. So because small x has been fixed, as player 2, we're facing a simple optimization problem, namely choose y maximizing uxy for our second player's payoff function. Now, there's a complication coming from the fact that these optima are not necessarily unique. But for the purposes of this video, let's pretend that this optimization problem always has a unique solution. So what that means is that player 2 has an obvious kind of optimal strategy, choice of y given every x, namely this thing. So this thing is a rule that will associate a choice of y to every possible x. So it's a function from x to y, apart from the thing that we're hand waving that this thing might not be unique. So note that this thing is a strategy for player 2. It's a choice of move for every possible observation that they could make. So now we can switch perspective and put ourselves in the shoes of player 1. So this is why it's called backward induction, because we're starting with the second player and now we're doing the first player. So we assume that player 2 is going to play optimally, which means that they're going to play the strategy F. So what that means is that we know that whatever X we play, player 2 is going to respond with F of X. So what that means is that as player 1, we are also facing a simple optimization problem, namely this thing. We want to choose X that optimizes this function, which we can write in an expanded form as this. So what that means you can see here that player one has to kind of solve player two's optimization problem kind of as a sub problem, because player one wants to calculate how player two is going to respond, and for that player one needs to put themselves into the shoes of player two. So this calculation method is called backward induction. We'll come back to this in a few videos time. So an example of this kind of interesting example is the fair cake cutting protocol. Suppose we have two players who want to cut a cake fairly. There's a known kind of protocol for this. Suppose the two players don't trust each other and they both want to optimize the amount of cake that they get. The protocol for this is that one player is going to cut the cake and then the other player is going to choose which of the two pieces that they want. So we can model this as a game in this sense, where the first player gets to choose an element of the interval from 0 to 1. So this models kind of the point along the cake at which they cut. So it's just suppose that this is a rectangle and they're going to cut it. And then player two gets two moves, namely to choose the left piece or the right piece. And you can write down a payoff function for this situation by this kind of thing. So if player two chooses the left piece, then player two gets the size of the left piece, which is x, and player one gets the size of the right piece, which is 1 minus x, and so on. So this is the point where we formalize that the players are trying to optimize the amount of cake that they get. So we can solve this problem. We can apply backward induction to this payoff function. So if we suppose that player one makes some cut, small x, then player two is trying to choose either left or right, whichever piece is bigger. Namely this thing. If we apply, right, so if player two chooses the left piece, then they're going to get x. If they choose the right piece, they're going to get 1 minus x. And the solution of this thing is we choose the left piece of x is at least a half, and the right piece of x is less than or equal to a half. And here I'm again hand waving that this need not be unique, because if x is exactly equal to a half, it doesn't matter, but let's ignore that. So this is an elaborate way of saying player two chooses the bigger piece always. So what that means is that player one wants to maximize this thing. And if you plug this f of x back into the payoff function, we end up with this thing, namely, so if x is smaller than 1/2, then player one is going to get x because player two took the bigger piece, which is 1 minus x. And if x is bigger than 1/2, then player one is going to get 1 minus x because player two took the biggest piece, which is x. It turns out that this is, in this case, this is equivalent to player one wants to maximize the size of the smallest piece, which explains why this probably looks somewhat familiar, because this is very similar to the problem we have of calculating max-min strategies last week. But I think that's just because this happened to be a zero-sum setting. In general, these are two max and max. It's just that because this is zero-sum, this max kind of behaves like a min. So what this means is that player one's solution of this optimization problem is to choose x equals 1/2. That's the thing that maximizes this. So that is to say, the solution to this is that player one makes an actual fair cut.